Hello everyone, my name is Jared Chester, and my group did software security for the final project. And today I'm just going to talk about our improvements we made to AFL fuzzing and just give you a general idea as to how fuzzing works. So to start out with, just want to give you an overview of the presentation. We're going to start with talking about what fuzzing is, in particular what AFL is and what it accomplishes as a fuzzer. And along the way, I'll just highlight some areas of potential improvement. And then I'll discuss our group's actual improvement, including what environment we tested it in, our experimental setup, and the criteria that we used to determine our outcome. And then I'll actually show some test results, make some remarks about it, and enumerate on some possible improvements to be made to the experiment. So to start out with, just want to talk about briefly what fuzzing actually is and where it lives in the development cycle. So to start out with, it lives in the testing stage because fuzzing is a testing metric. And particularly, it's used for security testing in that the way it works is you take input data and you throw it into your program with the hopes that it will crash it. And if it does, you sort of record that data down so that you can eventually, patch things into your program to fix it. And so just a more standard definition, essentially it's an automated test where, like I said, you take some sort of data, you input it into your program and just monitor what it outputs. And as a result, you sort of get an idea as to how your program behaves across a pretty wide range of data. So in particular now, the AFL fuzzer is described as a mutation-based black box fuzzer. And what that essentially just means is you give it an initial input, and all subsequent inputs that get run are some mutation, some permutation of that initial input. And black box basically means it doesn't care what your program does, as it just cares about what it outputs. So the innards are really not that important. It's more of what happens output. And how it works at a high level, it's very simple. You basically seed it with an initial test case. It puts it into this queue, which is used to manage all test cases that will be run. And it takes some input off of the queue. I'll discuss how that's determined shortly. It mutates that input using various techniques, which I'll also be discussing. And it just throws it through your program and records if there's any interesting behavior. And if there are behaviors that are interesting, it will just dump it right back onto the queue, and you'll repeat the process and mutate that one. It's important to note, though, that the fuzzer does support source code repository fuzzing. We chose to do binary files just for ease of use, but both tests are completely valid. So one of the most important parts of the fuzzing process is the input selection, in particular the initial input, because this is what determines basically the quality of your test, meaning you want to give it the best data up front so that it could mutate that in ways that will tell you the most about your program. So your initial input should always look like data that the program would normally expect to see. So if you're going to fuzz a video like imaging software or a video processing software, you don't want to throw it an MP3 audio file in the fuzzer because that doesn't really tell you how it handles, video data. So the input initially is very important. But of course, after that initial run, you need to determine what tests you're going to run next. And so the way AFL handles this is they do a probability. It's probabilistic. And I just took snippets of the code base to show you. So 99% of the time, you're going to run an interesting input that hasn't been ran already. And I'll discuss how interesting inputs get generated. But just know that there are differences between an interesting input and just a standard input. And so 99% of the time, we're going to spend time running the interesting stuff. But there are cases in which you don't have anything interesting in the queue yet. And so you need to separate the time that you run and decide what test case to run. And so AFL chooses to separate it in this way. So 75% of the chance, if there's nothing interesting in the queue, we're just going to run something that hasn't been run already. And then 5% of the time, we're going to run an uninteresting input that has already been run. So we're sort of double dipping there. And you can get away with that because there is some non-determinism, which I'll talk about later. But that's the breakdown. And this is our first improvement that could be made. You could mess around with these percentages, and you can definitely change your initial input. and you'll see pretty drastic changes in terms of testing. Another really important phase is how you generate interesting input and basically how you tag an input as interesting. So AFL does this based on a scoring system. So the first thing that they do is they just take the average execution speed and the average bitmap length, which essentially is just the length of the input string, and they multiply them together. And that gets a number, obviously. And then they ask the question, are new bits generated in this input string? Like, has testing yielded a new input potentially? If the answer is yes, then the score gets bumped. And then lastly, one of the more important metrics is, were there crashes? Because that's the whole point of fuzzing, is to determine what crashes your program. So if there was a crash, that almost guarantees we're going to get put onto the interesting queue. And the way it sort of divvies out these scores is it does like a table where, based on certain criteria in your execution speed or your bitmap length, it'll add or subtract or multiply by certain factors. And this is sort of the second area of potential improvement that you could make, in that you could change the way scoring works, the weighting and stuff like that. And I believe actually AFL Fast does something similar, where it sort of fudges around with the scoring system to determine what is interesting. Because remember, 99% of the time, we're going to be running these things. So, determining what is interesting versus what is not, you kind of want to have it pretty restrictive so you're not wasting computation time. And then finally, one of the last important phases is actually mutating your input. So like I said, you seed it initially with something, and then these things run on that and all subsequent inputs. So there's two phases. There's a deterministic phase that AFL offers and a non-deterministic phase. And in the deterministic phase, there are various tests. I'll just briefly describe them very quickly. So simple bit flip, you basically walk your input string bit by bit and flip 1 or 2 or 4 byte chunks at a time, or bit chunks depending on the test. And then in the arithmetic increment or decrement, you just add 8, 16, or 32-bit numbers or subtract them from your string in various places. And then there's the dictionary, which is basically a collection of sub-inputs that you then amalgamate. AFL sort of like amalgamates them together pseudo-randomly to generate more inputs. Still deterministic because the dictionary is obviously finite. And then lastly, we have the non-deterministic testing. That's sort of where you actually see the most interesting paths get generated from, just because they churn through tons and tons of paths at a time. And in particular, random havoc, you'll see as a candidate for which this occurs. You see a lot more paths get generated from it. But this is sort of how mutation happens. And the order in which mutation occurs, like non-deterministic versus deterministic, does actually change the way the test runs. So this is another example of a potential area that you could, improve. You can improve your criteria for random havoc. You can improve the ordering of things, etc. But just wanted to enumerate that for you as well. So now I just want to briefly show you an example run through, and I'll just sort of commentate over like what it looks like. So this is actually running on an Ubuntu virtual machine. I'll get into the specs a little bit later, but this is an example run on our experimental group, meaning these are the changes that we're applying. So I'll just run through it and describe to it. So the first thing that we're going to show you is that this is a mounted virtual drive. So I'm just going to highlight what that means there. Basically, it's a virtual disk, and I'll describe again later what that is in our experiment. And so now we're just going to go to that directory, and we're actually going to invoke the AFL fuzzer. And so the process of actually doing this is you first need to build the source code using some AFL builder. In this case, we chose an AFL Clang builder. Just don't really need to know the inner workings of that. But that's how we build the program. It puts certain hooks in there for AFL to use. But right now, we're just passing in parameters for, first of all, what input we're going to seed first. And so that's the I, the dash I. That is the initial input. The dash O is the output. The time, T is, time between hangouts. So how long do we have to wait? And then we actually pass it the program to fuzz. And then this is the output that gets generated. And so there are certain things that are kind of important to look at. The first thing is right here in the cycle progress. This tells you what the ID of what you are currently fuzzing and how deep it is within the queue. That's the percentage there. And then there is the staging progress or the stage progress. This tells you what test you are actually doing. So this will go from, like I said, simple bits, byte walking, things like that. In this case, we're doing user extras, which is a dictionary, which I'll discuss later. But this will tell you sort of what test phase you are on, what mutation process you are on. And then down here is the amalgamation of all of your different strategies of fuzzing input and what yield that they have. And the yield in this case means total paths. That's sort of a big metric that you look at. And you can see in this fraction here, out of 6,144 like permutations, we've only found 2 of them to be interesting or to even look at. So that's what those metrics mean. And then top right, these are your overall results. Basically, how many paths have you discovered? How many crashes have you experienced? How many hangs have you experienced? And then down here, these 2 fields are really the only important ones. The pending favorite, these are, like I said before, the interesting inputs that we put onto the queue that haven't run yet. And then these are in pending, these are the total number of pending things in the queue. And so this will just run and run and run until you break it or like you close it out or it exhausts all possibilities. But sometimes you'll see in the now processing an ID with a star, and that just means that it's an ID that we have not deemed interesting that's running. So that happens, like I said, 75% of the time if there's nothing interesting in the queue. So that's just just some semantics as to what this outputs. But that's sort of the demo. So now I'll go back into the actual explanation of some things. So I'm going to discuss now what we decided to improve. And after an extensive amount of research, we sort of landed on the idea of, AFL is maintained by professionals in the field who dedicate years of their lives to researching extensively. And so we felt like any source code changes that could be made were probably not going to happen in the short amount of time we had for this project over the semester. So we decided that any changes that need to be made will probably have to be outside of AFL itself. So that really leaves us 2 options: the operating system and the initial input that we give it. And so we did both of those things at once because we observed that AFL is a fairly I/O intensive process, meaning it reads and writes to disk constantly for inputs and outputs. And so if you can speed that up, you'll probably experience some gains in some field. And then lastly, we discovered that dictionaries, as I described before, are a better way to kind of bring out more crashes. And I'll explain why shortly. So, in our experiment, to describe it, we kept our environment the same, obviously. We kept it on Ubuntu in a virtual machine. The processor was a 4-core, 8-thread processor. We kept the RAM the same as 4 gigs. And we let every test run for exactly 1 hour. And what we actually tested from the Lava M suite, those 4 programs, and then 2 from the Fuzzer suite from Google. We didn't get to do a lot of those from the Google suite because there's like 28, and we just ran out of time. So as a result, we only got 2. But our control group, sort of how we ran our experiment, so we ran all of those programs on an SSD for an hour with no dictionary, just a standard SSD, and we recorded those results straight from AFL. And then in our experiment, we ran everything on the virtual disk, including the fuzzer and the fuzzing program, the program where we're going to fuzz. And we used a dictionary to see the initial input and just recorded the results in the same way. And so the criteria at the end of the day for this to be a failed or successful experiment, we basically said, do we increase the total paths discovered? Do we increase the number of crashes that we find? And lastly, do we increase the number of executions that we do throughout the entire fuzzing process? So those are our metrics. And now I'll discuss, how we managed to do those things. So the first thing in speeding up execution, we decided to use a virtual disk. In particular, we used RAM disk, which keeps memory in RAM, which is obviously much, much faster than going to a hard drive or an SSD for data. And what we ended up seeing were, execution speed was obviously faster for the most part. And as a result, though, paths discovered varied a little bit. And I'll discuss in our results why that may have occurred. And then the other thing that we did was the dictionary. And the way that we basically did it is we did some research on how to generate dictionaries. And the way that AFL uses these dictionaries is it uses them in the input manipulation stage, mutation stage, really. And we want to provide stuff in the dictionary that will lead to more meaningful mutations down the line. So we sort of tailored it to a specific application, which means every dictionary was different based on each application, with the idea that with this sort of tailored input, we could generate more behavior that would lead to crashing. And we actually managed to do that. So we found no crashes in any of the testing we did without the dictionary. And we actually found in some programs a significant amount of crashes and more interesting behavior. There is a caveat, however. With the dictionary, you spend less time generating new paths and more time exploring currently favored paths. So you'll see in those graphs shortly that we suffer a little bit in total paths, but what we gain really is a lot of crashes and a lot of behavior that's interesting that gets generated. So now these are the graphs. So the way you read them, I put them in sort of column order. So each column represents a specific program. And this is the same throughout all of these graphs. The orange color represents our experimental group, basically running it on the virtual drive and using a dictionary. And the blue is just the bog standard, run it on without doing anything else. And as you can see in the base64 case, we suffer in total paths, like I mentioned before, but we gain a lot in total executions. And the most probably important gain is we actually find somewhere in the range of like 22 crashes, whereas before we found no crashes. So like I said, the dictionary provides you a way of sort of getting out more interesting behavior, but at the behest of losing like total paths discovered. That overall number decreases. In MD5 sum, we see sort of different story. We see a neutral effect of total paths. We don't find really any crashes with our dictionary, but we still gain a little bit in our total executions. And then in the unique program, we don't gain much in total execs, but we actually increase in total paths. And a way of sort of understanding why that may have occurred is perhaps our dictionary wasn't strong enough. And so the inputs that we were generating weren't necessarily resulting in more like longer runs of a certain input. So as a result, more and more and more input was ran with less favored inputs being generated. And then just the last couple of graphics, we see that in Who, which is the last program we did in Lava M, a really dramatic decrease in total paths. We actually see like a fourth of the paths discovered, but we see a dramatic increase in total executions and in actual crashes. We see like 150 something crashes, which really definitely proves that the dictionary is useful in finding crashes, but will definitely hinder your ability to find new paths because you spend more time running favored paths from the dictionary than you do actually exploring new ones. And then in the JSON situation, these are both, the last two are both from the Google Suite, and we see either sort of null results or results that are inconclusive because one explanation could be that because the Google Suite contains applications that are perhaps more polished, larger, and more complicated, the time that we allotted to run didn't really allow the experiment to bring out anything meaningful. So as a result, we see, sort of inconclusive information from these two particular programs. So in conclusion, sort of wrapping everything together, overall, we see that our total executions increased pretty much across the board. Again, taking into account the Google suite, there's a sort of asterisk there. But in general, our executions increased. We also found crashes. We found more crashes because initially we found 0. And we can attribute that to the dictionary and having more tailored input data. And then, again, the total paths seem to decrease because of this dictionary, the introduction of this dictionary. We see that we don't generate as many paths, but we do generate more crashes and interesting behavior. So in general, improvements varied, yes, in both degree and significance, and some explanations for that. Like I said, the Google suite may have included, more advanced programs with larger code bases or entry points, and the time maybe was a factor. Also, randomness in testing in this case is always a factor because there is some non-determinism, like within AFL itself. And then dictionaries, like I said, they lead to more meaningful outcomes, but they really, really make you suffer in total paths. So that's the sort of outcome from our experiment. And we can conclusively say we increased total executions and we increased the number of crashes. We just did not increase the total number of paths. And so briefly, I just want to talk about possible improvements for this experiment. So first of all, ideally, we would love to run the full Google test suite. There's 28 programs in there with a ton of data that could be generated. That could either solidify this or sort of go against it. We just did not have time to run all 28. And also, by the same token, running each program through the fuzzer for like longer periods of time. We've seen in literature that they run it for hours, sometimes days at a time. And so perhaps doing that would yield either more extreme results in favor of our hypothesis or perhaps sort of level things out, depending. And then lastly, of course, spend more time creating dictionaries. I think if we really spent, we had a lot more time to do this sort of research into the dictionaries, we could really pull out a decent number of crashes from these programs. And I think dictionaries are a very big improvement to the AFL fuzzer that we've discovered. But in terms of everything else, that sums up our experience and our improvements. Thank you.